Alright, so for today's video, I wanted to go over evaluating limits analytically. So we'll talk about what that means in just a bit. But just to start off this lesson, I just want to kind of just refresh on the different ways to evaluate limits. So far, throughout this past week and last week, we have been investigating how to evaluate limits numerically using a table. So if you refer back to your guided notes on the first page, we actually used a table of values to help us find the limit numerically. So we have done this already. And then we have been focusing a lot on looking at graphs and trying to find the limits using a graph. So these are the two different ways that we have been talking about. So finding and evaluating limits numerically using the table and graphically. So for our next important part in evaluating limits is what we call evaluating limits analytically. And what that means is we're basically just using algebraic properties to help us evaluate limits. So all the stuff, all of the knowledge that we have learned back in Algebra 1, in Algebra 2, and a part of pre-calculus is really going to help us evaluate limits analytically using our knowledge of algebraic properties. So let's jump right into the lesson for today. If we refer back to our guided notes, this is page 10. So once again, we'll be talking about evaluating limits analytically. So let's jump right in here. If you look at this table right here, they give you 3 different basic limit rules. Let's just go over them really quick. I always think it's best to go right into the examples so that we can get a sense of how these limits should work. For number 1, we have the limit as x approaches c of some constant, and that'll just be equal to the constant itself. And we'll look at that in example number 1. If we go over to number 2, the limit as x approaches c of x. In this situation, we'll just plug in our c value in for x, and that'll be our evaluated limit. Next up is the limit as x approaches c of x to some power n. All we'll do is plug in our c in for our x, and this will be our limit. So let's look at example number 1. For these examples, they tell us to evaluate each of the following limits analytically. And please recall, analytically is just really just telling us to use algebra to help us out. Okay. So let's use our algebraic skills to help us figure out example number 1. So in example number 1, they give us the limit as x approaches 3 of a constant, which is 5. So this 5 right here is the function that we're working with. So if you wanted to on the side, you can say that the function that we're working with is y equals 5. And for these types of limits, I think it's helpful to really think about what's happening graphically. So I'm going to real quickly just sketch this constant function, y equals 5. Almost done here. So y equals 5 should look something like this. A horizontal line. All right. So now let's look back at our limit. So our limit is telling us to approach 3. So the first step you want to always do when you're evaluating limits is to make sure that you test the left-hand limit and the right-hand limit. Okay. So for this problem, we'll look at the left-hand limit and the right-hand limit. So if we refer back to this graph, as we approach x equals 3, from the left-hand side, we'll actually stop at this point. As we approach x equals 3 from the left-hand side, what y value are we approaching? In this case, we'll be approaching the y value of 5. So the left-hand limit will be equal to just 5. Same thing for the right-hand side. As we approach x equals 3 from the right-hand side, we will also approach 5. Okay. So therefore, the overall limit, the limit as x approaches 3 of 5, is just equal to 5. All right. So in the future, whenever you're just given a constant and they're asking you to find the limit, it'll just be equal to the constant itself. And that's what we basically proved in this problem. So hopefully that makes sense. Let's go over to example number 2. In example number 2, they give you the limit as x approaches 2 of 4x squared plus 3. There are different ways to approach this problem. For right now, at this point, I want to just go step by step. But at some point, we'll be able to just directly plug in our x value. But for right now, I want to go step by step, just to make sure that we're following our limit properties. So for this one, I'm just going to rewrite the limit they gave us. 4x squared plus 3. Awesome. And then if we go back to our properties of limits, using the sum property, we can distribute this limit into each one of these terms. So that is also equal to the limit as x approaches 2 of 4x squared plus the limit as x approaches 2 of 3. And then, if you really wanted to, we also have another property here. We have the scalar multiple property of a limit. So we can take out this 4 and put it on the outside. So this is also equal to 4 times the limit as x approaches 2 of x squared plus the limit as x approaches 2 of 3. All right. And if we look back at our properties here, we can just plug in our value that we're approaching in for x. So let's take advantage of that. Here in this case, let's focus on this limit. This is equal to 4 times, and we'll plug in 2 for x. 4 times 2 squared plus. And then if you look at this, this is actually directly related to what we did in example 1. The limit as x approaches 2 of a constant. So based on what we did in example 1, we can conclude that this limit as x approaches 2 will just approach 3. So this will evaluate to 3. Okay, we're almost done here. At this point, all we got to do is just simplify. So we have 4 times 4 plus 3. So yes, which is equal to 16 plus 3, which is equal to 19. Okay, so these aren't too difficult. At some point, we can just plug in our x value and get the same answer. But once again, we have to go through these properties first, and then in the future we can just plug it in. Okay, so for now I want you to make sure you go through this work. All right, let's go on to example number 3. In example number 3, they want us to find the limit as x approaches 1 of this function. So we have some type of quadratic expression on the top, and on the bottom we have a x plus 1. So my biggest tip here for you, is just try plugging in the x value that you are approaching. Okay, so I always recommend that because sometimes we are able to evaluate the limit directly without having to really factor. And we'll talk about factoring in just a bit, but let's just plug in the x value that we have here. So here, the x value that we're wanting to approach is 1. So why don't we just plug it in to each one? So that would look like this. I'm just going to rewrite the limit as x approaches 1 of x squared plus x plus 4 over x plus 1. I'm going to be real specific here before we plug in. We can use the division property. So this limit can go to the top and the bottom. So you have limit as x approaches 1 of x squared plus x plus 4 over limit as x approaches 1 of x plus 1. And then now we can plug in x equals 1 into these terms. So let's go ahead and do that. So you should get 1 squared plus 1 plus 4 all over 1 plus 1. And you get 1 plus 1 plus 4 all over 2, which evaluates ultimately to 3. And there you go. Here in this case, I want to point this out. We didn't come across any problem here. But there are some situations where you might get 0 over 0. And we'll see that in just a bit. Okay. So in this case, all we did is we plugged in our 1 into our terms. And we were actually able to get a value out of it. So this would be our limit for example 3. So now let's go on to example 4. Not too hard. In example number 4, they want us to find the limit as x approaches pi over 2 of this trigonometric function sine of x. So if we go back to our properties, all we got to do is plug in a pi over 2 in for x. So let me just rewrite the limit as x approaches pi over 2 of sine x. I think it's always a good habit to rewrite the limit. And then, according to our properties, we can just plug in pi over 2 in for x. So we have this equal to sine of pi over 2. And then this is where you actually have to recall the unit circle. Okay, so you have to recall the unit circle. So let me pull that up real quick. I have it right here. Sorry about that. Let me minimize it. Put it over here. So the value that they're wanting us to find is sine of pi over 2. Please recall that if you look at the unit circle, pi over 2 has an angle of, is really an equivalent angle of 90 degrees. So at pi over 2, we are at the coordinate 0, 1. And please recall that when we're talking about the unit circle, the y-coordinate of this point, will be your sine value in the unit circle. So if you look at this point 0, 1, the y value is 1. So therefore, the sine of pi over 2 is equal to 1. And there you go. So it's important to be really comfortable with the unit circle. On the exam, they will not give you this unit circle. So what I recommend is to make sure that you memorize these values because they will help us a lot. So we just went through examples 1 through 4. And they're not too difficult. Just be real careful when you're plugging in values of x. All right, so let's go on to the next section. For this next section, we're talking about functions that agree at all but one point. All right, so if we look at this box, it tells us let C be a real number and let f of x equals g of x for all x not equal to c in the open interval containing c. Then, therefore, the limit as x approaches c of f of x is equal to the limit as x approaches c of g of x. So let's figure out what all this means. So if you recall, in today's warm-up after the quiz, I had asked y'all to recall the ways to factor the sum and difference of cubes. So we will just talk about it right now in example number 6. Before we get to example number 6, let's go over example number 5. So the key idea here is we're going to be using factoring to help us simplify limits. Okay, so before we talk about factoring, one thing I want to point out here is what happens if we directly evaluate and plug in x equals -3 into this expression. Let's go ahead and do that and see what happens. So I'm going to plug in -3 and for x just directly, and we'll see what happens. Okay, that'll equal 9 minus 9 over 0. 9 minus 9 is actually just 0 over 0. So we have a huge problem right here, right? We have 0 over 0. We can't work with this. And this is what we call the indeterminate form. Okay, so we'll talk a lot about indeterminate form at the very end of our limit section. But in this case, we have 0 over 0. So plugging in x equals -3 directly doesn't help us. And please remember, if you go back to example 3, we plugged in our x value directly, and we were actually able to get a value out of it. So that's good. But sometimes it's not always the case. Okay, so in example number 5, we have to take a different approach. And the approach here is to factor. So factoring is going to be super, super important. So if we look at this, I'm just going to go ahead and rewrite it. Over x plus 3. And we have to ask ourselves at this point, is there any way we can maybe factor this expression? And you'll figure out that yes, we are able to. So if you focus on the numerator here, x squared plus x minus 6, we are actually able to factor this expression right here in the numerator. So there are different ways to factor. I know that many of you have different ways of factoring this. The way I like to think about it is setting up some, what we call a sum and product puzzle. Once again, you don't have to go this route, but this is the way I like to approach it. The number on the top here is going to be your C value, so -6. The number on the bottom here is going to be the coefficient of the x term, so 1. So we're going to have, I'm going to write the multiplication up here and the addition. So the idea is we have to find two numbers that multiply to get -6. And when you add those two numbers together, you'll get 1. So in this case, to complete this sum and product puzzle, you'll figure out that these two numbers are actually going to be 3 and -2. Sorry, 3 and -2. So 3 times -2 is -6. And when you add these together, you'll get +1. So if we go back to our limit, we can simplify the numerator as this: x plus 3 times x minus 2. All right, all over x plus 3. And when we factor the numerator, let's see what happens. So you'll notice that we have an x plus 3 in the numerator and in the denominator. So we can go ahead and cancel these out. So now we can simplify our limit to this expression. Limit as x approaches -3 of just x minus 2. And then we can just plug in our x value. So -3 minus 2. And this limit should evaluate to -5. And this is your answer for example number 5. All right. So we'll talk more about this, but in this situation, we actually have a hole in the graph. So whenever we cancel a factor out, this is signaling that there is a hole present in the function. Okay, and we'll talk more about that, what that means in the next few sections. But for right now, I just want you to be able to factor, okay? So that is the key idea, being able to factor. Okay, so in example number 5, we were able to factor a quadratic expression. Now let's go on to example number 6. In example number 6, they tell us to find the limit as x approaches 1 of x cubed minus 1 over x minus 1. So I'm just going to rewrite the limit here. Limit as x approaches 1 of x cubed minus 1 over x minus 1. All right, so if we refer back to the warm-up in the morning, we talked about sum and difference of cubes. So I'm just going to go ahead and refer back to those algebraic formula that we referred back to. So we had two different expressions it was x cubed minus y cubed. And we can factor that by saying x minus y times x squared plus xy plus y squared. So this is the difference of cubes. This is how we factor a difference of cubes. And then the way we factor the sum of cubes is this. So we have x plus y times x squared minus xy plus y squared. Okay, so these will allow us to factor our expressions, and this is actually relevant in example number 6. So please make sure that you're able to recall these factoring methods for difference and sum of cubes. Okay, so let's look at example 6. Right away, if you look at the numerator, we have x cubed minus 1. That is actually a difference of cubes. So I'm going to focus on x cubed minus 1 on the side. So I'm going to write it over here in the bottom, x cubed minus 1. That is just the same thing as saying x cubed minus 1 cubed. And if we follow our formula for factoring the difference of cubes, this is actually equal to x minus 1 times x squared plus x plus 1. All right. So now that we factored the numerator into this expression, we can go back and plug this factored expression back into our numerator. So this is equal to the limit as x approaches 1 of x minus 1 times x squared plus x plus 1 all over x minus 1. And then similarly, if we think about what we did in example number 5, here the x minus 1s cancel out. All right, so you're left with the limit as x approaches 1 of x squared plus x plus 1. And then now we're actually able to plug in our value of x equals 1. So we have 1 squared plus 1 plus 1. And that'll evaluate to 3. Okay. So once again, the reason why we had to factor using the difference of cubes is because if we just look at this limit by itself and plug in 1, you'll notice that if you just directly plug in 1 into this expression, you'll get 0 over 0, which is once again the indeterminate form. So because of that, we're unable to work with this expression. So the only other way to work with this limit is to be able to factor x cubed minus 1. And then that allowed us to cancel out the x minus 1s. And then ultimately we were able to evaluate and plug in our 1 in for x. And ultimately we got 3 for our limit. And that's pretty much it. Hopefully example number 6 made sense. And example number 5. One thing I want to point out here though, I cannot emphasize this enough. If you look at our process for example number 5, we made sure we kept that limit throughout the whole thing until we got to the last step where we plugged it in. That is super, super important. I cannot emphasize how important that is. You have to make sure that you carry the limit as you're simplifying along the way. And if you look back at example 6, that's exactly what we did here as well. So we kept that limit notation all the way through until we plugged in our x value. So you have to be consistent with the limit notation along the way. All right. So, real quickly, let me just go over the homework problems. The homework problems you should be able to do based on what we talked about. Okay, so if you refer back to the finding limits homework that I gave y'all today, one note, I'm gonna require y'all to complete the odd problems, okay? So keep that in mind, just the odd problems of the homework assignment. So if you look at the homework assignment, the first page, questions 5 through 21, all the odd, you should be able to do based on what we just talked about. If you look at the second section, you should be able to do questions 27 to 35 based on what we talked about. If you look at the third page, you should also be able to answer 37 and 39 using the properties of limits. All right, so just use the given values that they give you for the limits to help you figure out each of those different limits that they want you to find. And then if you go down to question 41 through 46, I'm sorry, I apologize, 41 through 45, you should be able to also answer those based on what we talked about. And for questions 47 through 62, so if you look at that page, at this point, you should be able to only answer 47, 49, and 51, okay? So let me just write those down. I apologize. Let me write those down. So for, once again, the finding limits homework, remember we're doing the odd problems. You should be able to do 5 through 21, 27 through 35, 37 through 39, 41 to 45, and for the other part, you should be able to do 47 through 51. And please remember that we're talking about the odd problems, okay? So hopefully this video helped out. If you have any questions, please feel free to reach out to me at any point. I'm always happy to help you all out. And I hope you have a great rest of your day.